Hello students, in this video we'll show that a limit of a function of two variables exists using the arithmetic-geometric mean inequality. Let's show that the limit as xy approaches 0, 0 of x squared y over x squared plus y squared converges to 0. So this limit is going to converge to 0. And so we've seen problems like this before where we plug in different trajectories and we see that the limit along different trajectories exists, or if it doesn't exist, prove the limit doesn't exist. But let's get an intuition for why this limit might exist. The numerator of this is of order 3. It's homogeneous of order 3, which means it's going to 0 in some sense at a cubic rate, whereas the denominator is going to 0 at a quadratic rate. So we expect things to be going to 0 faster in the numerator than the denominator. Now, how do we formalize that? What we'll do is the following. We're going to estimate our expression, and we're going to try a sandwich between two things going to 0. So what we'll do is we'll look at 0, and that is clearly less than or equal to the absolute value of the function that we're considering, over x squared plus y squared. And what I'll do now is I'm going to factor out one of the x's over here, so that's the absolute value of x, and then I'll have the absolute value of x times y over x squared plus y squared. And now the idea is the following. So I can drop the absolute value in the denominator over here, so I'm just going to have absolute value of x times absolute value of x times y over x squared plus y squared. And here, we'll make our use of our arithmetic-geometric mean inequality, the AM-GM inequality. It is a very, very powerful tool in mathematics. What it states in this very, very simple case is the following. It states that x times y, in absolute value, is less than or equal to x squared plus y squared over 2. Now this may look a little bit mysterious. There's beautiful geometric proofs of this, but for this case it's so simple we can actually just multiply by 2 to prove this. How would I prove something like this? I would just multiply by 2, and I'm trying to show that this is the case, x squared plus y squared, and I'm really trying to show nothing more than just 0 bigger than or equal to x squared minus 2 absolute value x times y, and then what? And then plus y squared. And this thing over here is exactly just a perfect square. This expression over here is just absolute value of x minus absolute value of y, quantity squared, because when you square an absolute value, you can just get rid of the absolute value. So this exactly is going to be x squared, that's going to be a y squared, then you have 2 of the cross terms, and of course anything squared is greater than or equal to 0. So by reversing this reasoning over here, if we reverse this reasoning, we'll arrive at the AM-GM inequality. Now how does AM-GM help us in this problem? Because now I'm going to use the AM-GM in this estimate over here. So this is less than or equal to by AM-GM. AM-GM. I'll keep the x by itself, and I'm going to replace this x squared by y squared by x squared plus y squared over 2, all over x squared plus y squared. And so now this x squared plus y squared is in the numerator and it's in the denominator, so it will cancel out. So this whole thing is less than or equal to x over 2. And so we've just proven is the following. So we now have this. We now have 0 is less than or equal to the absolute value of our expression, x squared y over x squared plus y squared, and that's less than or equal to absolute value of x over 2. And now as I let x and y go to 0, what do I see? I see that 0 is less than or equal to the limit as x times y goes to 0, 0 of the absolute value, what we want. And that is going to be less than or equal to the limit as x, y go to 0, 0 of just the absolute value of x over 2. Well, as x and y go to 0, x goes to 0. So our expression, the absolute value of our expression, is tending to 0. But an expression's absolute value tends to 0 if and only if the expression itself tends to 0. So from this, we can conclude that the limit as xy tends to 0, 0 of our expression x squared y over x squared plus y squared is equal to 0. So in this way, we prove the limit exists. And most limits like this, when you can actually count the degree of homogeneity of the numerator and denominator, can be handled by AM-GM or some slight variant of it. Thank you very much.